Today, fluids. Here's how fluids work. We can define the idea of a density of a fluid. I like to do that first. Density is used with the Greek letter rho. So I'm going to say, some people like the rhos like this, which is also fine. But the key fact about rhos is they don't have any straight edges, like P's would. We're going to have P's for pressure, and we're going to have rhos for density. So make sure that they are clear in your head. Density is defined as mass over volume. And again, we have an issue with notation. This is a capital V. Notice it doesn't have any wings, whereas this would be velocity. This will be volume. All right. And well, we can use this definition of density for all sorts of cool things in fluids, but first let's discuss some typical densities. Name something that's not very dense, right? Air. Super. Good job. The density of air. Oh, I thought I said I'd use the other one. Maybe I'll be switching back between them. Sorry. The density of air is about 1.29 kilograms per cubic meter. Whoa, that's a lot. That's a kilogram in a cubic meter of air? Did you think it was that substantial? I guess that's a little bit of a surprise. What about the density of gold? Well, that's a lot more massive. Can you imagine a cubic meter of gold? It turns out a cubic meter of gold is a whole bunch of kilograms. 19,000 kilograms. How much money would that be? That's an awful lot of money. Wow, put that in the comments. What about pressure? Pressure is another cool characteristic of fluids. So let's jump into this kind of with both feet. I want to consider pressure, but before we get into it, I want to define something called atmospheric pressure. Atmospheric pressure is 1.01 times 10 to the 5th newtons per square meter. So it's force divided by area, and we can just jot that down here. Pressure is, the definition of pressure is force divided by area. So if we continue, I could say that this is 1.01 times 10 to the 5th Pascals. That's the SI unit for pressure. And it's a super tiny unit. You notice that our atmosphere, which is not particularly squeezed, in my experience, it doesn't feel very squeezy, right? But it's 1.01 times 10 to the 5th Pascals, 100,000 pascals in our little atmosphere? I guess so. Okay. And I guess here's my next thing. I want to get you a bottle or a cup or something, and here it is. It's a cylinder, and there's going to be a fluid in it. We could put water in it for you if you want. Water goes like that in there, and the height of the water will be h. And the area of this cylinder, I'm going to call the area of the top of the cylinder A, and of course that's going to be the area of the bottom of the cylinder also. And I want to investigate the pressure at the top and the pressure at the bottom. Now the pressure at the top, that's just atmospheric pressure, right? The pressure at the bottom is going to be higher because there's water on top of it. So our goal in this little bit right now is to try to figure out how pressure changes as we get deeper inside of a substance. So we can do that by looking, instead of looking at the pressure directly, let's look at the force. I want to say that the total force on the top of the water is atmospheric pressure times the area over which that atmospheric pressure acts. And by the definition that we have here for pressure, we can certainly solve this for force and see that this is a trivial statement to say it's pressure times area, right? So we've got the force up at the top. The force at the bottom, though, the force at the bottom is a little trickier. Can we agree that the force at the bottom, on the bottom of this cup, will be the force that is acting on the top of the water plus whatever the water is doing specifically to the bottom of the cup? So I'm going to say that it's force top plus this new quantity, which is the weight of all of the water, and that's just m times g. So if I continue along this line of reasoning, I've got the force at the top, and I want to figure out what m times g is, but I'd like to use this definition of density to solve for m. So I'm going to get that the mass of the water will be the density times the volume of the water. Okay, so this is plus, whoa, instead of writing m, I'm going to write rho v, and so I can write rho g v, and this will be the force from the weight of the water. I'm going to go, well, no, this is good. Let's see if we can figure out then the pressure at the top. The pressure on the top is simply the force at the top divided by the area, and that is trivially the pressure of the atmosphere. No problem. But the pressure at the bottom is a little bit more interesting. The pressure at the bottom is the force at the bottom divided by the area. And so if I take this, that's going to be the force at the top divided by the area. That's atmospheric pressure, just as before, plus this strange quantity, which is rho GV divided by area. Rho GV divided by area. V is the volume of the water. Tell me what the volume of the water is. Okay. The volume of the water, oh dang, we've got an area and we've got a height. The volume is area times height. So if I plug that in, I'm going to get the pressure of the atmosphere plus, this is volume is area times height, so I'm going to get the areas to cancel, and it's going to be rho GH. Cool, let's put a box around that sucker. This is the pressure at the bottom of some depth of water. So the pressure is the pressure at the top plus rho GH. This is the density of the water. This is the acceleration of gravity, and that's how high the water is above you. All right, this leads to such cool effects as buoyancy and that thing called a barometer. Yeah, let's draw a barometer. Let's get into this. Here's a barometer. A barometer is a very cool device that has a cylinder shape, and there's a larger cylinder that's somehow held in place up here. But the cool thing is up at the top of a barometer, it's a vacuum. So let me see if I can continue drawing this thing and get it so that it looks kind of good. There we go. That goes behind, and we need to have some water in here or something. I guess it's often done with mercury. Water would be kind of a nasty solution to have here. I'll bring the water around and say that the water is in the bottom of this thing. And there's also water, there's water all the way up here, up inside this guy. And this is water, and this is water. Maybe I should crosshatch it. Yeah, there we go. This is water, all this is water, and we've got water in front of here, and water in here as well. What's up here? Up there? Nothing at all. We've taken a cup, filled it with a dangerous fluid called mercury, and plopped it upside down. And the question for you is, why doesn't the mercury all run out? It would certainly decrease its gravitational potential to run out of there, but it doesn't, and I'll tell you why. The only reason it doesn't run out is because the atmosphere is pushing down on it out here. The atmosphere is pushing down on this surface out here, which prevents this fluid from leaving and spilling out the bowl. If you took this into space, the mercury would all float out. But the fact is, the atmosphere is causing it not to be there. This is a barometer, and here's how it works. A barometer is used to tell us the pressure, and you know that there are some units of pressure that are called millimeters of mercury. What a stupid units of pressure. It has to do with a barometer, though. It has to do with the height of this column of mercury. So I'll define that height to be an H. We said it was water, but we're going to actually address it as if it's mercury, and then we'll have water as a challenge at the end. So I want to say that the height, oh dang, remember this equation? We know the pressure at the bottom is the pressure at the top plus rho GH. And this is the density of what? The air or the fluid in which we are? This is the density, in fact, of the fluid. So in our case, it's the density of mercury right here. So we're going to take the density of the mercury. Oh my goodness. Can we find out what H is based on the actual pressure? I think that we can. I think that we can. So what is the pressure right here? What is the pressure right there up at the top? Well, we know the pressure at the bottom. The pressure at the bottom has to be rho g h, right? And the pressure at the top, dang, this is a vacuum. The pressure up at the top is in fact 0. So we say pressure at top equals 0. Pressure at bottom equals rho times g times h. This is rho for mercury. Rho for mercury, and that's the pressure at the bottom. And oh man, can we solve for h? Let's just do it. Wait a second. If this is the bottom here, and it's open to the atmosphere, the pressure at the bottom is also equal to the pressure of the atmosphere. And this is an important equal sign. So I'm arguing that we can then solve for h. The height of the mercury is going to be atmospheric pressure divided by, well, I guess it's divided by rho times baby g. And if you do this, you plug in these numbers. I happen to know the pressure of the atmosphere, and I'm going to leave that as a problem for you. The pressure of the atmosphere is 1.013 times 10 to the 5th pascals. And the, oh man, we've got the density of mercury. Density of mercury is 1.3595 times 10 to the 4th kilograms per cubic meter. And I also know that baby G is 9.81 meters per second squared. What a mess. If you take all these numbers and plug them into here, you will get the answer. And that's a very important answer because that's another way of specifying atmospheric pressure, because we plugged in atmospheric pressure here. So let me talk a little bit about barometers. The idea is if the pressure of the atmosphere goes up, then what will happen to the height of this column of mercury? Can you answer that? What would happen to it? Would it go up or down? And if the pressure falls here, then what would happen to this column of mercury? Would it go up or down? If I put this into a vacuum, what would happen to the height of that column of mercury? Now, that's all great. Here my final question is, find H for a water barometer. Some of these have been built, but you'll see why they are not particularly convenient when you find H for a water barometer. Good luck. What about pressure? Pressure is another cool characteristic of fluids. So let's jump into this kind of with both feet. I want to consider pressure, but before we get into it, I want to define something called atmospheric pressure. Atmospheric pressure is 1.01 times 10 to the 5th newtons per square meter. So it's force divided by area. P's for pressure, and we're going to have rho's for density, so make sure that they are clear in your head. Density is defined as mass over volume. And again, we have an issue with notation. This is a capital V. Notice it doesn't have any wings, whereas this would be velocity. This will be volume. Today, fluids. Here's how fluids work. We can define the idea of a density of a fluid. I like to do that first. Density is used with the Greek letter rho. So I'm going to say, some people like the rho's like this, which is also fine. But the key fact about rho's is they don't have any straight edges, like P's would. We're going to have, all right. And, well, we can use this definition of density for all sorts of cool things in fluids, but first let's discuss some typical densities. Name something that's not very dense, right? Air. Super. Good job. The density of air, Oh, I thought I said I'd use the other one. Maybe I'll be switching back between them. Sorry. The density of air is about 1.29 kilograms per cubic meter. Whoa, that's a lot. That's a kilogram in a cubic meter of air? Did you think it was that substantial? I guess that's a little bit of a surprise. What about the density of gold? Well, that's a lot more massive. Can you imagine a cubic meter of gold? It turns out a cubic meter of gold is a whole bunch of kilograms. 19,000 kilograms. How much money would that be? That's an awful lot of money. Wow, put that in the comments. What about